First speaker is Geoff Haynes, who works for Inspirit Ventures. Geoff is an industry veteran in power semiconductors, founded GaN Systems, Inc. Thank you, Geoff. I've got my notes here. Which became part of Infineon's cool GaN technology. So absolutely industry-leading technology, widely used today. And congratulations on your lifetime achievement with power semiconductors. Currently works for Inspirit Ventures, advising companies on lots of areas of power innovation. So thank you, Geoff, for speaking today. I think we're going to enjoy your talk.
Well, we'll see. It might be quite comical because I've only got 10 minutes, so I've scripted this thing. It's the only way I can get through it. And I'm already wasting that time, but if I try and do it on here, I won't be able to read it, and I've still got to click through it. Anyway, so Geoff Haynes started a GaN company 15 years ago. We made perfectly good transistors 10 years ago, a lot of them winning in the Google Little Box Challenge. But do you see them around in power? Yeah, they're all over your laptop adapter, but in power beyond 10 kilowatts, it just doesn't happen. So what I want to look at is why silicon carbide looks like it's beaten the whole thing. Okay, so this chart's from Yole. It clearly illustrates the eventual importance of compound semiconductors with respect to silicon power transistors. Switching speed drives power density and efficiency by reducing the size and weight of the storage components in switched power converters of all types. The silicon carbide market has exploded in response to the legislated demand for conversion to electric power for transport. But it isn't faster switching that's driven this market expansion. It's smaller, high-current die operating at higher voltage and temperature in legacy electrical systems. Compatibility with existing electrical designs, transistor packaging, and manufacturing practices were all essential for rapid adoption. Anticipated manufacturing volumes have driven manufacturing investment, and market demands have driven cost expectation. And still, the market's growing for silicon carbide because they've started to figure out that it's just not small enough or power dense enough, so it's got to switch faster. But ultimately, you run out of that because you can't switch that transistor any faster. So for me, there is suddenly an opportunity for GaN. If we could do the same thing that silicon carbide transistor does, but do it much faster, that'd be great. But unfortunately, we've got to do quite a lot of things to even be able to use those transistors in a system, and that's what's held it back. There isn't a connection between the devices and the systems. The devices change everything in the manufacturing value chain if you want to get the value out of them. I'm not saying here that GaN is going to overtake the world in power, but there's some areas where high voltage and power density are absolutely critical, and that's where GaN is going to really make a difference. So let's look at each of them. The first thing is I talked with, is he here? I talked with the CSAC this morning, and they're saying, well, yeah, we can get 1200 volts, but I have to put two of them together. And yeah, you'll do it much more efficiently, but if you start talking to a designer of something, it gets complex. He doesn't want to play. So this is only going to happen when we get 1200 volt transistors. But finally, we do start to have some. They're all promises. You can't actually get them unless you go to power integrations, and they're all already making lots of things with, that's great, 614. I'm still on time. That's great. They can make 1700 volt converters because they've got their own transistor and they put it in their own system. Lower inductance, thermally efficient modular packaging. That's the first thing. We've got to get the heat out of these things. They're tiny. Getting the heat out of them is really difficult. They're nice and efficient, So they're not generating a lot of heat, but we're sticking them in small packages, so it's getting really hot, and we can't get the temperature out of the device itself. So we've been working on that problem. RAM Innovations in the UK has been doing a lot of work to take the transistors and put them inside that little box and making the whole thing much smaller. That's a 60 amp half bridge. I had one in my pocket. Well, I won't pull it out. It's about an inch square. And we make them in volume. You print them all. So it's something that can be quite cheap. But now we've got a switching cell. I've got to optimize it. I better catch up with my notes here so we don't go on too far. There we go. Clearly, these assembly techniques do not sit comfortably in conventional power electronic manufacturing facilities. To accelerate adoption, it's important to be able to provide a component subassembly that can be simply adopted in high-volume electronic assembly lines. Most power converters are made up from not transistors, but half-bridges. Once we can provide a simple-to-adopt integrated switching cell, a half-bridge, that anybody can use because we've taken care of all the problems of how to build them and how to use them, then we have a chance to go forward. But actually, that's only the start of the problem because we've left out an awful lot of stuff here. There's all the digital stuff that has to control these things. It's much more complex, but we can put the controller on our little board, and even that starts to disappear. The first thing that we can do with those is take that little block and put a controller on top of it. And we can make any one of these things in our little block by putting the appropriate controller in it. So now I'm starting to look at how do I design my circuits differently. Oops, yes. Interference is going to be a problem. As soon as I say I'm switching fast, people say, I can't do that, it makes too much noise. And in a car, that's a disaster. So here's a solution to that. This is actually a Nottingham University student's project, where he looked at taking one of these little modules and looking at screening, filtering, and partitioning in that module to achieve 100 dB reduction in the noise. If I switch fast, the components that I need to do that, the filters become much smaller too. It's actually easier once you know the answers. So, once we've got those switching cells, we can rethink the way we build a converter architecture. Here's something like TTPI, a company we spun out of Nottingham University. And what they've done is two optimized switching cells have been combined with a high-frequency transformer to provide a dual-active bridge. A number of these assemblies are arranged in both series and parallel combinations to achieve the input and output operating specifications of a bidirectional DC to converter. It's actually the same thing that we saw in that diagram of a system, except it's a very different way of achieving the solution. The complete converter assembly, because it's now producing sine waves, can be stuck together vertically, lots of them, to get higher voltages, and in parallel to get much more current. Let's go back to that transistor. I said we need a 1200 volt transistor. Sheffield University and a little company in Japan have been working for the last, how many minutes have I got? Oh, that's enough. To produce a transistor that's far more reliable because we don't have the charge gradients in the channel because we're using a whole gas to balance our electron gas, and it's on an insulator, not on the silicon that they forced us to put our transistors on because they had to be cheap. And so I don't have a breakdown to the substrate, and I can now have high voltage devices. So that has been developing over nearly 10 years now. We've had 2 goes at getting EPSRC research for it. Finally, the university gave up and gave the professor some money to do it. We proved that we can make a 3,000 volt bidirectional switch. Now, our co-worker in Japan who do all the epitaxs and work on the sapphire substrates, they were discovered by Toyota. And Toyota said, wait a minute, this is a game changer. And they came up and they told Sanken, look, you need to regenerate your power electronics semiconductors. You need to invest in this company. So our Japan collaborator is now part of a big semiconductor company. But we have shared IP, and we've got 3 more patents to put on top of it that they don't have. And we have the solution of how do you take this high-frequency transistor and put it in a system. So I think I can enable the desire that Gunny put out, that he wants to work JETRO and TechWorks together, go talk to the 2 governments and say, let's get on with this. Now, here's the real challenge. I've got no time, but I'm going to take a little bit of question time. The real challenge here is no one of these markets would drive a foundry. You need hundreds of millions of devices. But actually, every power market needs this little converter. And if you design it right, you can put it into any converter system. You might have to style it a bit to fit, whether it's in the military or whether it's in aerospace, but everybody could use it. Now, the only way we'll ever have volume is the way silicon carbide got there. Everybody thought they had to have it because Tesla said. And I think we need to turn that around. We need the industry to say we have the solutions. Let's, for goodness sake, get on with it, because it's going to take 5 years to have production. But we don't want then to wait for another 5 years to prove it's reliable, and then another 5 years to stack up how we use it. We have to do all of that in parallel now. Thank you.
Geoff, thank you for your presentation and your passion on the subject. It's fantastic.